So what we're going to do is we're going to now look at how we can determine the set of quantum numbers for a given electron as based on the information given to us from Schrödinger's wave equation. We refer to this as our electron configuration, and we're going to have two things, and we'll use different terminologies. If we want to represent the electrons in a given orbital down to our ml value, then we'll use what we call our horizontal energy diagrams. But if we want to only represent the number of electrons in a given set of orbitals, so for example, if we want to determine how many electrons are all in our 2p orbitals, then we'll use what we call our electron configuration. And we'll use both of these because both of them allow us to determine different things about the atom, anywhere from its relating to both its chemical and physical properties. One of the things that I have to keep in mind is the Aufbau principle. And what this says is that I fill orbitals of lower energy before I fill orbitals of higher energy, which makes logic sense. So here are the orbitals required to explain the entire periodic table listed in terms of their energy. And so we have our 1s, our 2s, our 2p, so that makes sense. That follows along with what we saw in our chart. Our 3s, our 3p follows along in our chart, but then the 4s comes before the 3d, because it takes less energy to put electrons in the 4s than it does to put them in the 3d. Then after the 3d comes 4p, then 5s, then 4d, because it takes less energy to put it into 4d than the 5s, then 5p, then 6s, and then 4f, then 5d, then 6p, then 7s, 5s, 6d, 7p. You will need to have a way of remembering this basic order. And we'll talk about a number of different ways that you can remember it, but the first one we're going to look at is using this little chart-like structure. And so if you made a series of columns where you listed the orbitals, and you had the energy levels and then the orbitals, and we had them in rows and columns, and then we drew a series of diagonal parallel lines, so it goes through it like this, then if we start reading from the top, we go 1s, then we go 2s, then we go 2p, 3s, 3p, 4s, then 3d, 4p, 5s. And so these lines help us to remember the order in which our orbitals appear. Okay. Now this may seem complicated to you. You might be able to just remember the original order, but later on we'll come up with another strategy as well after we've done a number of these to practice. Another thing that we have to keep in mind when placing the electrons, and this is in particular in our horizontal energy diagrams, and when we're placing them at the orbital or ml value level, what we have to remember is we have to remember that orbitals of equal energy will each get one electron before we place a second electron in that orbital. So for example, when we have the 3p orbitals of any energy level, the px, py, pz, I place one electron in the px, one electron in the py, and one electron in the pz before I place a second electron in the px. Okay. So let's take a look at a couple of simple elements, and we'll look at 3 or 4. So the first one, let's start off with the easiest, hydrogen. Hydrogen has one electron, and so what we can do is we can look at its horizontal energy diagram. And so our first energy orbital that gets an electron is a 1s. And because my 1s only has one ml value or one orientation, it only gets one dashed line. So I have an n value of 1, an l value of 0, my ml value of 0. One digit, one line. Now it has one electron, so I denote that electron with an arrow pointing up. And we always put arrows pointing up first. Okay, and so this now represents its ms value. So now I have my N, my L, ML, MS. Okay. Likewise, we can look at helium. Helium has 2 electrons, so we start off with our lowest orbital of lowest energy, as stated by Aufbau principle, 1s. Okay, I can place my first electron in it. Now I have a second electron, so I place my second electron, and it's would be denoted by an arrow down. So this tells me that the first electron has an N value of 1, an L value of 0, an ML value of 0, and MS value of plus 1/2. And the second electron has an N value of 1, an L value of 0, ML value of 0, and MS value of negative 1/2. So we can see the 4 quantum numbers for each of my electrons in these diagrams. Let's look at a bit more complicated element, nitrogen. So we follow Aufbau principle. My first energy level that gets electrons is the 1s, and so I have 2 electrons to place in there because nitrogen has 7. So now I still have 5 left. So now I bring in the next orbital of lower energy, which would be my 2s. I can place 2 electrons in that. So now I've used up 4. I still have 3 left, so now I bring in the orbitals of next lowest energy, which would be my 2p. And we can see here we have 3 dashed lines because this represents our 3 ml values for a 2p orbital, because it can be -1, 0, 1. And I follow Hund's rule by placing 1 electron in each of them before I pair them. And so this would be my horizontal energy diagram for nitrogen. And finally, if we look at iron, we know that this electron configuration up to here takes us to 7 electrons, so we can just start counting from here because we have 26 in total to place. And so I'm going to place the rest here. So now up to this point, I've placed 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So next would be my 4s. That brings me to 20. And then after 4s, 3d, and I have 1, 2, 3, 4, 5 orientations. We place 1 electron in each of them, and then we pair. And so that would be my horizontal energy diagram for iron. Okay, and it allows us for any electron to know its combination of 4 quantum numbers. So for example, if I looked at this electron, I could see it has an N value of 3, an L value of 1, an ML value, we will say arbitrarily that this one is positive 1/2, or positive 1, sorry, and an MS value of negative 1/2. Likewise, if I look at this electron right here, I can see it has an N value of 3, an L value of 2, a M value of, we'll arbitrarily call this one positive 1/2, positive 1, sorry, and an MS value of positive 1/2. Now, this is a lot of information, and this amount of information can be used to explain a lot of the properties of an atom, but sometimes this is more than we need to explain. And so what we can do is we can simplify where we look at the number of electrons in a given set of orbitals, and so we just look at how many are in each subshell. And so if we look here, for example, an example of magnesium, and so what this does is allows us to express our principal quantum number, our N value, our L value, and how many are in those L values. So for example, we go with our hydrogen, which had 1 electron in the 1s orbital, then it has an electron configuration of 1s1. Helium, which had 2 electrons in the 1s orbital, would be 1s2. Nitrogen, which had two electrons in the 1s orbital would be 1s2. Add 2 electrons in the 2s orbital, so it'd be 2s2. And it has 3 electrons in total in all of its p orbitals, so it'd be 2p3. Okay, and if we look at iron, it has 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, 2 electrons in the 3s, 6 electrons in the 3p, 2 electrons in the 4s, and it has finally 6 electrons in the 3d. So that would be its electron configuration.